All right, here we have the 6.8.3 homework, 1440, 1442, 1444, 1446, and 1448. Starting with 1440, we have the equilibrium N2 gas plus 3H2 gas makes 2NH3 gas. Our initial molarities are 0.60 molar, 0.76 molar, and 0.48 molar. We need to know which direction this is going to shift, so we need to solve for Q. Q is 0.48 squared over 0.60 and 0.76 cubed, which is 0.87. So the reaction quotient 0.87 is less than the K value given in the problem, 1.2. So since Q is less than K, it's going to shift to the right, which means NH3 will increase and N2 and H2 will decrease. 1442, we are told that we have some unknown quantity of NO2 gas, and initially we have none of the NO and O2 gas. It's going to shift to the right, of course, so it's minus 2x plus 2x and plus x for the change. So we have the initial amount of NO2 gas, which we don't know, minus 2x for the NO2, 2x for the NO, and x for the O2. Now they tell us that the pressure of oxygen at equilibrium is 0.25 atmospheres, so we know the O2 is 0.25 atmospheres, which means since that one's x and NO is 2x, that the pressure of NO must be 2x or 0.5 atmospheres. Now plugging those two numbers into Kp, 158, we can actually solve for the equilibrium pressure of NO2 because it's on bottom squared. So I know this says concentration of NO2, but it actually should say pressure of NO2 squared is going to equal that on top multiplied together is 0.0625 over 158. So the pressure of NO2 squared is 0.000395557. Square root both sides, you get the pressure of NO2 equals 0.020 atmospheres. All right, here's 1444. I2 gas makes 2I gas. We have 0.0456 moles of I2 and a 2.30 liter container. So that's a 0.0198 molar initial concentration of I2, and of course 0 for I, minus x for the change for I2 plus 2x for the change for I. 0.0198 minus x for I2 and 2x for I. So when we plug those into the K expression, we have 2x quantity squared, or 4x squared, over 0.0198 minus x equals 3.80 times 10 to the minus fifth. Now this is setting up to be a quadratic equation problem because we're going to have an x squared term and an x term and a constant once this is all factored out. However, I would like to introduce you to the 5% rule. The 5% rule is an approximation technique that can be used in these problems to avoid having to do a quadratic equation. So here's basically how it works. If your k is small, and this one is 3.80 times 10 to the minus fifth, then the shift to the right is going to be very small. So in this case, x is going to be very small. So we don't expect much shift to the right because k is going to be small. So if x is small, then potentially it could be negligible compared to 0.0198. Now by negligible, we mean less than 5%. So what we can do is we can say that 0.0198 minus x is basically the same as 0.0198. So we're actually just dropping the minus x out of the term 0.0198 minus x. So if we do that, this becomes a much simpler problem because then all we have to do is multiply both sides by 0.0198 and then divide both sides by 4 and then take the square root. So that gives us x equals 0.0043 molar, which means if we plug those back in, and by the way, 0.00043 molar is less than 5% of 0.0198, so our approximation is correct. So the pressure of I2 is 0.0198 minus 0.0004, so that's 0.0194 molar at equilibrium. And the pressure of I atoms is 0.00086 molar. All right, so here's 1446. CO2 gas plus H2 gas makes CO gas plus H2O gas. We have equilibrium values given in this problem, not initial values, but equilibrium values of 0.086 molar for CO2, 0.045 molar for H2, 0.050 molar for CO, and 0.040 molar for H2O. If we plug those into the K expression, because we are at equilibrium, we get a Kc value of 0.52. So then they inject some carbon dioxide and raise the 0.086 molar for CO2 all the way up to 0.50 molar. So that is going to be an external perturbation that is going to upset this equilibrium. So we are going to now say that the new molarity, 0.50 molar CO2, is simply an initial molarity, which is then going to allow a change to reach equilibrium. So 0.50 molar is our new molarity for CO2, 0.045 molar for H2, 0.050 molar for CO, and 0.040 molar for H2O. Our change is, because we now have too much CO2, is minus X, plus X, and plus X. So 0.50 minus X, 0.045 minus X, 0.050 plus X, and 0.040 plus X. Plugging those values into Kc, we get the products over reactants, 0.050 plus X, 0.040 plus X, over 0.50 minus X, well, missed a decimal there, and 0.045 minus X. Now, Kc equals 0.52 is not really small, so we can't just drop the plus X's or the minus X's in this problem. Instead, we would have to do it the long way. We would actually have to use some kind of solver on a calculator, or actually expand it all out and collect like terms and figure it all out with a quadratic equation. So for the purposes of this, I'm just going to say that some magic or mathemagic actually occurs, and we magically are able to determine that X equals 0.025 molar. I'm going to skip that math because it's not a math class, and AP would never make you do this problem with this much math in it. They would give you some kind of shortcut like square rooting both sides or using the 5% rule. So just consider it to be okay to just say that the value for X based on this algebra is 0.025 molar. So since that's true, we can now determine the molarities of CO2, H2, CO, and water at equilibrium by plugging them into 0.50 minus X, 0.045 minus X, 0.050 plus X, and 0.040 plus X. Okay, and our final problem, 1448. We have the same equilibrium again. H2 gas plus CO2 gas makes H2O gas plus CO gas. This time we're given 0.80 moles in a 5-liter container, so that's 0.16 molar. Initial molarity 0.16. So 0.16 molar for H2, 0.16 molar for CO2, 0 molar for H2O, and 0 molar for CO. We need to shift to the right, minus X, plus X, and plus X, 0.16 minus X, 0.16 minus X, X and X are our equilibrium values. Plug those into the Kc value at this temperature, 4.2. We get X squared over 0.16 minus X quantity squared equals 4.2. Now this is one where we can square root both sides. We get 2.05 equals X over 0.16 minus X. Bring the 0.16 minus X over to the left. We get 2.05 times 0.16 minus X equals X, which expands out to be 0.328 minus 2.05X equals X, or 0.328 equals 3.05X. So a little bit of algebra, but not as bad as doing a quadratic formula. So we finally get to the point where we have X equals 0.328 over 3.05, which is 0.11 molar. Plugging that back in up above, 0.16 minus 0.11 is 0.05 molar at equilibrium for H2 and CO2. and H2O and CO are X, so H2O and CO at equilibrium are